This section, 3.5, is all about calculating empirical formulas. And there's a couple of different things that we're going to be doing in this section. But the first one is fairly easy, and that is if we are given the percent composition of each of the elements in a particular compound, then we want to be able to calculate the empirical formula. There are three easy steps when we're doing this kind of calculation. One is that when given the percent composition by mass, all right, we change those percentages into grams. The idea behind this is, well, if we have 100 grams of a substance and it's, 53.45% carbon by mass, then it's 53.45 grams of carbon. So we can just take those percentages and simply turn them into grams. Then we will take those masses and convert them into moles. Of course, we'll use the molar mass of each element in order to convert the masses into moles. That's an easy calculation, something that we just did in the previous section. And then the third thing is that we're going to take the smallest number of moles. We're going to take those each of those moles and divide by the smallest number of those moles. So it's a way of getting our ratio. Ultimately, when we're calculating empirical formulas, we have to get the moles of each element and then divide by the smallest. And there's a lot of ways to do that, but for this particular type of problem, this is the way to do it. So let's look at an easy example. So here is a substance, para-aminobenzoic acid, also called PABA. It is composed of carbon, and it gives the percent, 61.31% carbon, 5.14% hydrogen, 10.21% nitrogen, and 23.33% oxygen. We now want to calculate the empirical formula of PABA. First thing is we want to change the percentages into masses. So we're going to take each of these percentages and write them down as grams. So 61.31% carbon is going to be 61.31 grams of carbon, and so on and so forth for the other elements. Now, if you're paying close attention, you will see that these percentages don't quite add up to 100%. They add up to 99.99%, and that is fine. That is just a little bit of rounding error in one of them, and that is not an issue. So that is not an issue. All right, now that we have those, our second step is going to be to take those those masses, and convert them into moles. So we'll convert the masses into moles. So our 61.31 grams of carbon will divide by the 12.01 grams of carbon per mole of carbon. That's our atomic mass that we will find on our periodic table. And that will give us 5.105 moles of carbon. Notice that I kept the same number of significant figures that we had in our original percentage and in our mass. For hydrogen, 5.14 grams of hydrogen, divide by 1.01 grams of hydrogen per mole of hydrogen, and then that gives us 5.09 moles of hydrogen. For nitrogen, 10.21 grams of nitrogen, we'll divide by the molar mass, which is 14.01 grams of nitrogen per mole of nitrogen, and that gives us 0.7288 moles of nitrogen. And then finally, for oxygen, 23.33 grams of oxygen, divide by the atomic mass, 16.00 grams of oxygen per mole of oxygen, and that gives us 1.458 moles of oxygen. Okay, so now that we've done those calculations, there's a couple of things that I want to point out. One is that you'll notice that we chose the mass of the element, the molar mass of the element, not the molar mass of like molecular nitrogen. So we didn't want to pick N2 here, we picked N. So when we're doing these empirical formulas, we're going to take the number that is straight off the periodic table. The other thing that I want you to note is that we've got 4 different numbers over here, and step 3 involves taking each of these numbers and dividing by the smallest. Well, our smallest clearly of these is nitrogen. So we're going to divide each of those numbers by nitrogen. Doing that is going to give us the subscript in the formula. So our subscript for carbon, which I had arbitrarily called X, is 5.105 divided by 0.7288. When we do the math there, those each have 4 sig figs. That comes out to 7.005, which we can round to 7. Now, sometimes it will be okay to round to the nearest whole number, and sometimes it won't. The way that you will determine whether it's okay to round to the nearest whole number is you can look if the difference is in the last significant figure, it's okay to round. If this were 7.335, that would not be okay to round. And we will see problems like that where it is not near a whole number. This one is obviously very close to 7, so we can round that to 7. The subscript for hydrogen, which I, again, arbitrarily had chosen the letter Y, we've got 5.09. So 5.09 divided by 0.7288, and that is going to give us 6.98. Since hydrogen only has 3 significant figures here, 6.98, our last significant figure, it's only different in our last significant figure, so it is okay to round that to 7. So these are both 7. For the next one, nitrogen. So nitrogen, again, I arbitrarily chose Z for that one. And 0.7288 divided by 0.7288. And of course, no calculator needed there. That is 1. And then, and one of these will always come out to 1 when you're doing this particular part of the calculation. And then finally, our subscript for oxygen, again, I arbitrarily chose W for that, 1.458 divided by 0.7288, and that gives us 2.001, which I think everybody can agree, that is close enough to 2 that we can round that to 2. So now that means that these are the subscripts in our empirical formula. So our empirical formula for CXHYONZOW is going to be C7H7NO2. Now you'll notice that for the 1 here, we did not put the number because if the number is 1, it is implied and we don't need to put the 1. All right, so let's do an example, and we're going to do number 32 on the in-class assignment. And I recommend that with this, you pause the video and attempt to do this on your own before I do it. If you get stuck, start to play the video for a little bit, and then pause it again to see if you can finish it. So that is my recommended technique for following along here. So step 1. Remember the steps. Step 1 is going to be to write these numbers that are in percentages, write them down as grams. Step 2 is going to be convert those grams into moles. Step 3 is to pick those moles and divide by the smallest, and then that will be our empirical formula. So here we've got carbon at 37.02. So I'm going to put 37.02 grams of carbon. All right, and I need to leave enough room here so that we can do the calculation. So I'm going to space these out a little bit. 2.22 grams of hydrogen. For nitrogen, 18.50. So 18.50 grams of nitrogen, and then 42.26 grams of oxygen. All right, so we're going to multiply each of these, or actually divide each of these by their atomic mass. Atomic mass for carbon, we've seen this one several times before, 12.01 grams of carbon per mole of carbon, and that is going to come out to some number. I'll go ahead and calculate that. Make sure this is all on screen here. So 37.02 divided by 12.01. And we get 3.082. 3.082 moles of carbon. At this point, I don't want you to worry about what these numbers are. A common mistake here is to say, oh, I can round that to 3. No, don't do that. That is a great way to get a really wrong answer. So don't do that. All right, so now for hydrogen. So hydrogen, we usually round it to 1.01. If you happen to have more than 3 sig figs here, then you'll want to go out one more significant figure and do 1.008. But on this one, we can do 1.01 grams of hydrogen per mole of hydrogen. And when we do that, so 2.22 divided by 1.01, we get 2.198. We're going to call that 2.20 moles of hydrogen. Again, we have 3 sig figs there. For nitrogen, 14.01. So we'll divide by 14.01 grams of nitrogen per mole of nitrogen. And so 18.50 divided by 14.01. And we 1.320. So 1.320 moles of nitrogen. And then finally for oxygen, let's see, oxygen is, what is oxygen here? Oxygen is 16.00 grams of oxygen per mole of oxygen. So 42.26 divided by 16, and that gives us 2.641. 2.641 moles of oxygen. All right, so we've done step 2. So step 1 was to write down these percentages as masses. Step 2 was to divide by each of the atomic masses to give us the number of moles of each element. And step 3 is that we're going to take each of these numbers and divide by the smallest of those numbers. Now, clearly, the smallest of these numbers is nitrogen. So for X is going to be equal to 3.082 moles of carbon divided by 1.320 moles of nitrogen. So 3.082, 1.320. All right, and we have 4 sig figs for each of those, so I'm going to write down 2.335. So 2.335. Now this is not close enough to an integer to round. Since we have 4 sig figs, it would have to only be different in the last significant figure to round that to 2. So this is going to be a fractional number, which means that we're going to have some multiple of these numbers when we get our empirical formula. So don't worry about that just yet. I'll show you how to fix that. But we're going to have to multiply that by some number to get us close to a whole number. So next, let's do hydrogen. Hydrogen, we use the subscript Y. Again, these are arbitrary. You can use any letter that you want. So 2.20 moles of hydrogen divided by 1.320 moles nitrogen. So 2.20 divided by 1.320, and we get 1.6666. We're going to call that 1.67. So 1.67 because we only have 3 sig figs there. All right, for nitrogen, this one's easy. We won't need the calculator for this. 1.320 moles of nitrogen divided by 1.320 moles of nitrogen, and of course that gives us 1. And then finally for oxygen, we're using the letter W there, 2.641 moles of oxygen divided by 1.320 moles of nitrogen. I think this one you can almost tell what it is without even without even doing the calculation. But of course, we'll do the calculation. 2.641, and we'll divide that by 1.320. And you'll see we get 2.001. So 2.001. I think we can all agree that that is close enough that we can round that to 2. So at this point, this is what we know. Our empirical formula is going to be some multiple of this. So our empirical formula, is some multiple of, and I'll put some multiple of C 2.335 H 1.67 N1O2. All right, now clearly the nitrogen and oxygen are okay because they are whole numbers, and we typically like whole numbers when we're doing this. But if we look at this, the carbon here, carbon and hydrogen, those are not okay. They are not close enough to a whole number. Now, there's a couple of different approaches you can take to this. One is you can say, well, what is 2.335 close to? And that's close to 2 1/3. And 1.67, well, that's close to 1 2/3. And so if you multiply by 3, you're going to have a good number here. But I'm going to go through it and just do one iteration after another. So I'm going to take multiply this by 2 and see what we get. So when we multiply by 2, I'll put times 2 here. So we multiply it by 2. So 2.335 times 2 gives us 4.67. Hydrogen at 1.67. So 1.67 times 2. And that gives us 3.34. And then nitrogen times 2 is 2. Oxygen times 2 is 4. As you can see, those are still not close enough to whole numbers to round. So that is not our answer. So then we'll just go to the next step, which is multiply by 3. And spoiler alert, this is going to work. All right, so when we multiply this by 3, so 2.335 times 3, that comes out to C 7.005. Well, that's definitely close enough to 7 for us to round. For hydrogen, 1.67, so 1.67 times 3, that comes out to 5.01. So 5.01. Well, that is, again, it's only different in the last significant figure, so that's close enough to 5 to round. And then N3O6. So our formula for this, our empirical formula, here, I'll go ahead and write this like this, is going to be C7H5N3O6. So C7H5N3O6. And I'm going to fix that little 3 there because that'll drive me crazy later when I'm looking at this. All right, so C7H5N3O6. Now, I'm sure there are multiple compounds that have this particular formula, but I wanted to pick something that is exciting that has this formula. And so the compound that I picked is this. So let me draw it out for you guys. I'm going to draw it out using the method that we would use in organic chemistry. All right, and the name that we have for this is that we would call this 2, 4, 6 trinitrotoluene. All right, so trinitrotoluene. Toluene is just this benzene ring with the methyl group, and then the trinitro, we have 3 nitro groups that are on there in the 2, 4, and 6 positions. All right, the more common name for this is TNT, and that is a high explosive that is used in that is used in certain munitions. So trinitrotoluene. There are other nitro-containing compounds that are also suitable for things like mining, and those would include nitroglycerin, and which is a component of dynamite. But the whole point of this is that this is an exciting explosive compound. Do not try to make this at home. And first of all, you won't have the facilities to do it, and you might blow yourself up. And second of all, you will be violating multiple federal laws. So take care of yourself and don't try to make this. But it is kind of cool here to see that explosive compound, we can get the formula for it from these percent compositions. All right, well, that is the empirical formula based on percent composition. So next, let's go back to the presentation, and we're going to look at doing combustion analysis. So we're going to look at combustion analysis. All right, so combustion analysis, this is a method where we take a compound and we burn it. And so when we burn it, we will produce carbon dioxide and water. And based on how much carbon dioxide and water we get, we can determine what the formula of that compound is. Now, this is a long type problem. This takes a little bit of time to do, and you need to be patient when you're doing them. So I recommend being very systematic about doing it, and two, to take your time and go through each individual step. Follow along with my video here, and we're actually going to do another one after this. So you're going to get lots and lots of practice doing this. So again, if you've got a compound that has carbon, hydrogen, and oxygen, and you burn it, the only two products that you're going to get are going to be water and carbon dioxide. And so I'm going to switch over just real briefly to the in-class assignment, and because we're going to be doing this particular problem, which is propylene glycol. And I know what the formula for propylene glycol is, but you don't at this point. And so we're going to say that CXHYOZ. And we don't know what that formula is going to be. We know that when we burn it in oxygen, and we're going to produce carbon dioxide and water. All right. Well, since the only things that we're going to produce are carbon dioxide and water, then we know all of the carbon that was in this compound is going to be converted into carbon dioxide. So if we can measure how much carbon dioxide is produced, then we can determine how much carbon was originally in our compound. Next, we're going to look at water. Well, all of the hydrogen that is in this compound is going to be converted into water. So if we can determine how much water was produced, then we can work backwards and determine how much hydrogen was in our original compound. All right. So let's go back and look at the combustion analysis page here. So we're going to determine, as I mentioned a second ago, we're going to determine the carbon from the mass of the carbon dioxide that was produced. We'll determine the hydrogen from the mass of the water that was produced. Unfortunately, since oxygen is in everything, we'll have to kind of work backwards to get the amount of oxygen that was originally in our compound. So, okay, so when we're setting this up, let's go back to number 3.52 here. So this is our in-class assignment here. All right, so a couple of things. Let's just go ahead and read it. A compound, propylene glycol, contains carbon, hydrogen, and oxygen, common additive for pharmaceutical and personal care products. That's extra information. Combustion of 4.214 grams. So we have 4.214 grams of propylene glycol produces 7.312 grams of carbon dioxide and 3.995 grams of water. What is the empirical formula of this compound? So what is the empirical formula? So I'm going to go through and show you the method for setting this up. And the method for setting this up is, if you can get that method, then that is going to help you solve this problem. So first things first is we're going to take the mass of carbon dioxide that is produced. So mass of CO2. And we're going to do a calculation to convert from the mass of CO2 to the moles of CO2. All right, mass to moles, we're going to use the molar mass. We're going to use the molar mass. For moles of CO2, we're then going to calculate the moles of carbon. Now, this is an important number, and because it is an important number, I am going to put a little star by it to indicate that it's an important number, and that I want to highlight that number as we're going through and doing this calculation. But then we need to do an extra calculation, and that is to convert that into the mass of carbon. And the reason that we need the mass of carbon is because there is oxygen in this original compound, the propylene glycol. If there was no oxygen in that, we wouldn't need to get the mass of the carbon. We would be like halfway to the solution. But we're going to need to get that mass and subtract it from this. All right. Now, before we do any of the calculation, let's set up the other part of this, which is for water. So we'll do the mass of H2O, and we'll convert that into the moles of H2O. We'll convert that into the moles of hydrogen. Again, this is an important number. You'll remember when we were doing the percent composition type problem, we had to get the moles of each element, and then once we got the moles of each element, we divide by the smallest. Well, we're going to do the same thing here, and so after this part of the calculation, we will now have the moles of hydrogen. So I have moles of carbon and moles of hydrogen. We need to do an additional calculation, which is to figure out what the mass of hydrogen in our compound was originally. Okay, we'll leave a little space here. So then we're going to want to do a calculation where we get to get the mass of the oxygen that's in our original compound. Well, this calculation, the mass here of carbon, tells us out of this 4.214 grams of propylene glycol, how much of it is carbon. And this one will tell us how much is hydrogen. Well, if we subtract those two numbers away from the mass of this, we'll get the mass of oxygen. So our mass of oxygen will be equal to the mass of CXHYOZ minus the mass of carbon and the mass of hydrogen. All right, we'll leave a little space there because we're going to do a calculation there. Once we have the mass of oxygen, we're then going to calculate the moles of oxygen. And that is our final number, our final important number. And so once we have that number, then we'll be able to divide by the smallest, and that will give us our empirical formula. So, all right, let me leave a little room for that. And then down here, our formula, so x, our subscript for x is going to be equal to well, we'll take the mass, the moles of carbon, and divide by the moles of the smallest. And then for hydrogen, we'll do the moles of hydrogen, divide by the smallest. And then for oxygen, we'll do the moles of oxygen and divide by the smallest. So we'll do that particular calculation down here. And then once we have that, we'll get our empirical formula. So there's a lot of steps here, but if you're systematic and you write out a plan like I just wrote out, then you will come up with the right answer. All right, so let's take the 7.312 grams of carbon dioxide. So 7.312 grams of CO2, and we're going to divide by the molar mass of CO2. Now, we've seen the molar mass of CO2 a couple of times here, and the molar mass of CO2 is 44.01. So 44.01 grams of CO2 per mole of CO2. So that tells us how many moles of CO2 we'll have at this point. Now, in every mole of CO2, we want to know how many moles of carbon we have. Well, since there's one carbon per molecule, that's just a 1-to-1 ratio. So this is hardly even a calculation, but it's a worthwhile thing to write down. 1 mole of carbon per 1 mole of carbon dioxide. And at that point, we're going to have a number. So let's go ahead and put that number in. So clear all that. 7.312 divided by 44.01. All right, times 1 divided by 1. And that gives us 0, and I put this in red, 0.1661 moles of carbon. All right. That is an important number, so I'm going to put a box around it. And I wrote it in red so that we could easily find it here in a moment. But we're not quite done here. We want to convert the moles of carbon. I'm just going to leave the number that's in the calculator here. We want to convert the moles of carbon into grams of carbon. And that'll tell us out of the 4.214 grams, how many grams were carbon. So to do that, we'll just take that number and multiply by 12.01 grams of carbon per mole of carbon. And so we'll do times 12.01, and that gives us 1.995. 1.995 grams of carbon. Again, what that number tells us is out of this 4.214 grams of propylene glycol, 1.995 grams of it is carbon. All right, let's do the same calculation, but with water. With water, we had 3.995 grams of H2O. We'll divide by the molar mass of H2O. The molar mass of H2O is 18.02 grams H2O per mole of H2O. So that tells us how many moles of H2O we have. Now we want to get the moles of hydrogen. So we want to see how many hydrogens are in each water molecule. That's 2. So we're going to have 2 moles of hydrogen for every 1 mole of H2O. And that's going to give us a 3.995 divided by 18.02. And then we'll multiply that by 2. And again, this is an important number, so I'm going to write it in red here. So 0.4434 moles of hydrogen. All right, so now we've got the moles of hydrogen. We do want to get the mass of the hydrogen, and so we're going to need to use the atomic mass of hydrogen. Since we have 4 significant figures here, I'm going to use 4 significant figures from the atomic mass. So I'm going to use 1.008. So we'll multiply that by 1.008 grams of hydrogen per mole of hydrogen. So again, I'm just going to leave the number that's in the calculator and multiply by 1.008, and that gives us 0.4469. So 0.4469 grams of hydrogen. Okay, so we now have got the mass of hydrogen and the mass of carbon. And so we can subtract those two numbers from the original mass of our propylene glycol. So from the original mass of our propylene glycol. So let's go ahead and do that calculation. So 4.214 grams minus 1.995 grams, and then also minus 0.4469 grams. And that is going to give us a number. So let's go ahead and clear all that. 4.214 minus 5 minus 0.4469. And you'll notice that the number that we get there is 1.7721. Thousandths place, 10 thousandths place. We're going to round that to the thousandths place. So I'm going to round that to 1.772. So 1.772 grams of oxygen. So now that we've got the mass of oxygen, we're just one step away from getting the moles of oxygen. So we'll take 1.772 grams of oxygen. We'll divide by the atomic mass of oxygen, which is 16.00 grams of oxygen per mole of oxygen. So 1.772 divided by 16, and that gives us 0.11075. We're going to call that 0.1108. So 0.1108 moles of oxygen. Okay, so now that we've done that, we now want to calculate the subscripts. So here we've got our moles of carbon, which was 0.1661, moles of hydrogen, which is 0.4434, and our moles of oxygen, 0.1108. We're going to divide by the smallest. Clearly, the oxygen is the smallest. So our subscript for carbon, we will do 0.1661 moles of carbon divided by 0.1108 moles of oxygen. Now you're going to see this does not come out to a whole number, which means, it means that we're going to have to do an extra step, but that's okay. So 0.1661 divided by 0.1108. And you'll see that comes out to 1.499. So 1.499. Now, you can probably figure out that that is supposed to be 1.5. And so we could potentially round that to like 1.5, but we'll deal with that in a second. So let's do hydrogen next. So 0.4434. So we used Y for the hydrogen. So 0.4434 moles of hydrogen. Again, I'm taking that number, the moles of hydrogen that we had up here. And then we're going to divide that by 0.1108 moles of oxygen. 0.4434 divided by 0.08. And you'll see that comes out to 4.002. Well, that is definitely close enough to the whole number 4 to round it to 4. It's only different in the last significant figure. It's not different here. It's different in that last sig fig. For our last one, this is not really a calculation, but we'll go ahead and write it down. 0.1108 moles of oxygen divided by 0.1108 moles of oxygen. And of course, that comes out to 1. No calculator needed there. So it looks like what we have as our empirical formula, all right, is we've got, and I'm going to go ahead and make that 1.5. So we have C 1.5 H4O1. All right, clearly some multiple, that multiple is going to be 2. So some multiple of this is going to be our formula. So our empirical formula for this is going to be C3H8O2. And if you look up propylene glycol, that is indeed the empirical formula for propylene glycol. Okay, so that is part A of this problem. And you probably want to take a break at this point. When I'm doing this one in class, I do this one, and then I have my students do the next one, and then I solve it on the board. You probably want to take a break and maybe walk around your room for a little bit, shake out your hands because you've written a lot of stuff here. We are going to go ahead and move on to part B of this problem. And part B of this problem is very similar. It's just that we have a different compound. All right. And so what I'm going to recommend is that you go through and you may back up a few seconds here and go look at that other problem and start to work out this problem using that other one as a template. All right. I'm going to pause the video and I'm going to write the setup for this problem with the video paused. All right. Well, through the modern miracle of pausing the video and writing these things down, I've set out the template for doing this. And I recommend that when you're setting these problems up, you do the same thing. That way, you're just focused on getting out writing down the calculations and doing the calculations, and you don't have to worry about. Okay, what am I using this number for? Because it's all going to be there together. So we'll start with the numbers. So we'll do the mass of carbon dioxide, 6.572 grams. Divided by the molar mass of carbon dioxide, 44.01 grams of CO2 per mole of CO2. And then 1 mole of carbon per 1 mole of carbon dioxide. And again, this is an important number. And so clear this, and we'll put 6.572. Make sure that's showing up. Yes, it is showing up on the screen. Divided by 44.01. And that gives us 0.1493 moles of carbon. It's not carbon dioxide. It is how many moles of carbon dioxide. But we're interested in the carbon. All right. And then we're going to multiply that number by 12.01 grams of carbon per mole of carbon. So we'll just take that, multiply by 12.01, and we get 1.793. grams of carbon. All right. Again, what these numbers tell us is that this tells us how many moles. It's one of the numbers that we need to know to solve the problem. So that tells us the number of moles, and then this tells us out of the 3.102 grams how many grams are carbon. And it looks like, wow, that's a lot of it. So we've got a pretty significant percentage of our compound is carbon. All right, next, let's do the calculation for water. So we have 1.012 grams of water. We'll divide by 18.02 grams of H2O per mole of H2O. And for hydrogen, we've got 2 moles of hydrogen per 1 mole of H2O. Okay. And again, that's because there are 2 hydrogens in every water molecule. So now what we want to do is we want to do that calculation. So 1.012 divided by 18.02, and then multiply that by 2. And that gives us 0.1123 moles of hydrogen. All right. And so now we're going to take that number and multiply by the atomic mass of hydrogen. So times 1.008 grams of hydrogen per mole of hydrogen. So times 1.008, and that gives us 0.1132 grams of hydrogen. Again, that tells us out of this 3.102 grams of our terephthalic acid, our original compound, this is how many grams are hydrogen. We're going to take those two numbers now, subtract them from this to get the mass of oxygen. So our mass of oxygen, 3.102 grams minus 1.793 grams minus 0.1132 grams. All right. So let's do that calculation. So 3.102 minus 1.793 minus 0.1132. All right, and that gives us 1.95 or 1. Let me rewrite that. 1.1958 grams, and then we're going to round that to 1.196 grams of oxygen. Okay. So now what we want to do is we want to convert those grams of oxygen into moles of oxygen. So we'll do 1.196 grams of oxygen divided by 16.00 grams of oxygen per mole of oxygen. So 1.196 divided by 16, and that's going to give us, so 4 sig figs, so 0.07475 moles of oxygen. All right, so now we've got all 3 moles. We've got all 3 moles. We've got the moles of carbon, the moles of hydrogen, the moles of oxygen. We'll look at those 3 and see which one is the smallest. Clearly, it's the moles of oxygen is the smallest, so we're going to divide each of these by the moles of oxygen. So for carbon, we'll do 0.1493 moles of carbon divided by 0.07475 moles of oxygen. So 0.17475. And the number we get there is 1.997. And I think everybody would agree that it's only different in the last sig fig, that we can round that to 2. For hydrogen, our subscript was Y, so 0.1123 moles of hydrogen divided by 0.07475 moles of oxygen, 0.11237475, and we get 1.502. And I think everybody would see that that is about 1.5. So we're probably okay. 1.500, it's okay. We can't round it to a whole number, but we know that we're going to have to multiply that number by 2. All right, and then for the final one, I write this calculation out even though you don't need to put it in your calculator. Moles of oxygen divided by 0.07475 moles of oxygen. And that, of course, comes out to 1. So our empirical formula is a multiple of C2H1.501. And so in order to get to whole numbers, we just have to multiply by 2 here. So our empirical formula, go ahead and write this in red. Our empirical formula is going to be C4H3O2. So C4H3O2. We're not quite done here. We've got something else that is that's interesting that is going on here, and that is that if we come back up here to the problem, it says, what's the empirical formula? All right, we just figured that out. So the empirical formula is the lowest whole number ratio. The molecular formula is the actual number of atoms, and the molecular formula is always going to be some multiple of the empirical formula. So the molecular formula could be C4H3O2, it could be that, or it could be C8H6O4, or it could be C12H9O6. All right, I'm multiplying these out in my head here, so I'm apt to make a mistake there. But the point is that our substance has a molar mass, the molecular formula has a molar mass of 165 plus or minus 5 grams per mole. So some multiple needs to fall within that range of 160 to 170. So the easiest way to do this is we're going to do a quick and dirty calculation. Here we're just going to do whole numbers for this. So I'm going to do I'll do 4 times 12 is 48, and 3 times 1, of course, is 3, and 2 times 16 is 32, and when we add those together, we'll get, so 3, 13, carry the 1, 83, so 83. So the formula weight of this is 83 grams per mole, and some multiple of that has to fit into this range of 165 plus or minus 5. Well, it doesn't take a whole lot of math here to figure out that if we double this, we'll get 166. We'll get 166. So that means that our molecular formula All right, and here I need to scoot up so it's all on the page. So, so there, 83 was the number that we got, and if we double that, we're going to get 166, and so that gets us in the range. So our formula is going to be double this, and our molecular formula is going to be C8H6O4, and that's going to give us terephthalic acid. And in case anybody's curious what that looks like, there's several different isomers of this, but I'm just going to do one of them. All right, and that is the formula for terephthalic acid. So 1 plus 6 more plus 1 more, that's 8 carbons, 6 hydrogens. So 1, 2, 3, 4, 5, 6. That's 6 hydrogens, and the oxygens 1, 2, 3, 4. That's 4 oxygens there. All right, there's one more quick thing that I want to do before we stop this section, and I'm going to go back to this. And so when combustion analysis is not the only tool for figuring out empirical formula. I've already shown you the percent composition, and that is one of our methods for doing it. Of course, the percent composition, there's no simple experiment that gives that to you directly. You usually, with percent composition, have to figure that out from other experiments. But there are a whole bunch of different techniques for figuring out how much of each element is in a particular compound. And usually what it involves, or always what it involves, is getting either the moles of each element or something that is proportional to the moles of each element. And so sometimes that involves taking it and burning it, like we do with combustion analysis. Sometimes it involves taking it and heating it up to such a high temperature that all of the atoms are turned into plasma, and then you look at how much the flame of that plasma absorbs. All right, and that's called atomic absorption spectroscopy. And there are any number of techniques that you can use to figure out what the empirical formula of a compound is. And so when you combine those techniques together, that's what allows you to get the empirical formula. All right, so many methods. You could do an entire semester on calculating empirical formulas and molecular formulas using instrumental analysis. So, all right, well, that is the end of this section, and next we're going to start with stoichiometry.